Thank you. Thanks for introducing me. Thanks for introducing the topic, static analysis for non-critical systems. So if anybody in the audience is developing safety critical systems, I'm so sorry, you might have heard most of the words I'm saying today. If you're not doing critical systems, if you're doing non-critical systems, there might be some new ideas in there on why these tools can and should be used independently of the criticality of the system you're developing. Just because it's nice for developers, just because they bring benefit, and not because some normative document forces you to use the tools that we have available. Use them because they have a purpose, they have a benefit. See? So, thank you. Let's go for the button then, if it doesn't want to do it my way. Let's have a little background first. So what's static analysis? What's it good for? What's the idea and how do these tools work? Second attempt, I'll give it 3. Come on. Okay. So let's see, what is static analysis about? In principle, let's do 3 important questions: the what, the why, and the where. The what, it's analysis of source code automatically by a tool, and we are looking at the source code as it is. We are not executing, we are not modifying, we're not doing anything to it, we're just looking at the source code. Different from testing, as in, with testing you see the executions that happen in your test cases. With the source code you see every possible execution, everything that could have happened, everything that could be in it, which might be more than you're interested in, but which also gives you a more thorough view on your system. Why? To ensure code quality. And you can now subsume everything you ever wished for in that code quality aspect, be it more security, more safety, more maintainability, better long-term support, what have you. We are finding interesting properties in the source code, and whatever you think is interesting is on you. And usually this is used in regulated markets: automotive, medical, industrial automation. Those are the areas that have some normative documents that, somewhat like law, prescribe you to do static analysis. But I'd like to argue, and hopefully PowerPoint argues with me. Screw this. This will restrict me a little, but we'll be fine. I'd argue you can use it everywhere, right? That's not a technology where you need to be in a restricted market, where you need to be safety critical. So let's give you a classification of static analysis tools. What can you have? And what you probably already have in use are linters, like the most simple kind of static analyzers, where you have purely syntactical checks. They look at the source code with the question, is this written in the way it should be written down? And you've all seen your IDE upon saving, reformatting your source code. In principle, that's a static analysis. It looks at the source code, finds interesting patterns, namely those that don't look like you want them to look, and makes them look differently. Then we have bug detectors, and they go for runtime errors. They go for runtime properties. Short remark, that guy just said he's not executing, and now he says runtime property. We're not executing, but we're trying to infer what could happen when it would be executed. And there you have all the properties like you're dereferencing null pointers, you divide by 0. At runtime, the type of a class is in a certain way such that the pointer doesn't work out. I'm pretty sure you've all hurt yourself when doing C++ at least one time, and you can imagine the possibilities there. Now with the bug detector, you go for findings which most likely imply errors. That is, if the tool reports, then there's a high chance of your source code being broken somehow. That's nice. That's immediately actionable. You can go and fix it. Usually that's not enough if you're in a safety critical area, because then you want these very conservative tools that say, If the tool cannot exclude the possibility of an error, then it will report. If you're an airbag or a braking system, most likely errors doesn't cut it. You want every possible errors. But you can imagine the conservative tool will over-report. It will give you false positives just for the sake of not missing an error. And to make the discussion a little more thorough, let's give you some key properties that the static analysis guys keep talking about. And that the first one is soundness. The tool does not report an alarm at a code location should imply that no error can in fact occur at that code location. That's a nice property to have, right? That gives you some assumptions about how your tool works, and it says there are no false negatives. If I'm close enough, it works. And there's completeness. That's basically just the other direction of that implication. An error cannot occur at the source code position implies the tool does not report an alarm at that location. Now you also have an interesting property, and that is you can trust the system that there is no bug where there is no message. And given these two properties, I'm pretty sure you can now imagine what you're all wishing for. You're all wishing for the tool that has both, right? Let's see how far I can walk and this will still work. The tool reports an alarm at a code location exactly when the error can occur at this location. Every time the tool raises the little red flag and calls for a human to come help, there is actually a problem in your source code. And what a beautiful world. Now, anybody of you who has done some studying in computer science has at least heard of the field that is complexity theory and theoretical computer science. And those are kind of the bad guys here, because theoretical computer science says you can't have these two properties at the same time. You can, but then you lose a third property, and that is the tool has to terminate. So it's your choice now. You can live in the beautiful world of having both soundness and completeness, but then the tool might just not terminate. Good trick, right? If you are trusting me on giving you the right message and I'm just not terminating if I'm not no, here we are. You cannot have these tools, it just doesn't work out. So, come on, I'm just staying here. So tools have to over or under approximate alerts. The conservative tools prefer false positives, but that gives you false alerts. The bug finding tools give you false negatives, that gives you missing alerts. And the good news is usually you have some kind of freedom, some degree of soundness can be configured. You can make the tools work for certain properties in the way that you want them to work. So which tool is the right one then for non-critical systems? I've mentioned the conservative ones. Those are for the safety critical areas where you cannot afford not to find a potential error. I can't say, but maybe at the end of my talk, you can decide for your project and maybe the property you're looking after, which of these is the right one that you are looking for. So I've promised there will be benefits to using these tools. What are the benefits? What do you have to gain? And do these benefits apply to non-safety critical projects? And I'm going to argue, yes, they do. Let's go for the first one, avoiding common mistakes in source code. Now, that's a simple C program, and since this is one of the first talks of the day, you might be a little tired. Let's exercise a little. So, left hand, if you have any idea what might be the output for these two questions. Come on, don't let me down. You all know macros. Okay? Right hand, if you have an idea what the analyzer should suggest to you. Okay, yeah, not bad. Let's see. So the precedence rules are not considered. The macro is pure textual replacement. It will take the 2 plus 3 and purely textually add it where the parameter is, and giving you 2 plus 3 times 2 plus 3, computing 25 and 11. And at least one of these is unexpected, or at least might be unexpected. I'm pretty sure those who had the right hand up expected that one. So what should an analyzer suggest? It cannot give you the right computation, but maybe an analysis system could look at that source code and suggest that arguments inside replacement and the replacement itself should be braced, right? That just ensures that the expression is computed correctly. So a static analyzer could look at all your macro definitions and pinpoint those that are unsafe. Let's get the participation rate a little higher here. What's the value of K? You're not compilers, I can tell, because you're humans. And compilers have no problem parsing that at all. It just works. But your fellow developers have a hard time looking at that, trying to figure out what exactly is going on here. Because there's nested code, pretty spaghetti-like. There's variables, names being reused. And that is confusing. I'm pretty sure if you get enough time to figure it out, you'll all find the value. But let's see. Anybody, any idea what could be a good suggestion here? A few people have ideas. And those are exactly the ideas you would write down in a review, right? If you do 4i principle before merging, you'd probably say what an automatic tool could say here as well. It's more of a slapstick now, I'm sorry. The variable name is used twice. The innermost is referenced, but there's also another one that's driving up the complexity. A tool could pick all of that up. And ending the debate on the PR, whether, I don't like it, it's too nested for me. You'd have a set of rules. A static analyzer would look at those and would determine, well, please avoid shadowing your variable names, or do not use overly nested structures. And you just turn it from a matter of taste into a tool is judging the quality of the source code, and giving you input where you could improve. Last one, just to exercise your minds a little, what's the value of result? And I'm pretty sure you all have some ideas. Some people still looking confused. Okay, everybody who has any idea what the tool suggests, do a backflip. You didn't see that one coming. But still, let's see, what's the value? You can compute it, but why is that code that is hard to maintain, hard to understand, that drives your fellow developers mad when they have to look at it? Well, the tool could suggest a few things here, which is local variables must be initialized. Why not? That would get the return case right. At the same time, the default branch maybe has to be defined, just to be sure. Or should there be no fall through if this is not just an empty case? I don't know. That's for the projects to decide. But that's a common way to actually produce errors. So maybe it should be forbidden and maybe it should be found automatically. Let's go for another benefit then. I've promised multiple benefits and I got a few. We can enable continuous refactoring. And of course, you all know refactoring, you all do refactoring probably. So why continuous? Let's do a little charting exercise here. The functionality of a software grows roughly like that. That's what we as developers are paid to do, right? We increase functionality of software over time. That's the greenish line because that's what we want to do, that's what we want to achieve. Now, given I had a red marker and I would somewhat arbitrarily give it to somebody of you to draw the line that represents the complexity of that same software system. Exactly. At least the guy in front here has the right idea, and I'm pretty sure most other people have. That will be, of course, something that grows exponentially. We all hate it, yeah? But that's just what happens. The complexity grows faster than functionality, and that's exactly what makes refactoring necessary, because at some point, you reach a level of complexity that makes maintainability utterly impossible. That's happening especially for the people in safety critical areas, and that's happening for people that have long maintenance periods. For a medical device, it might easily be possible that you have to support that firmware for 20 or 25 years, which means none of the original developers is still with the company while you're maintaining. So you got to have some maintainability, some readability. And we know how this is achieved, right? We do refactoring. And refactoring makes the complexity roughly go like this. It piles up, and then you take it down, and it piles up, and then you take it down. At least that's what the book of computer science tells you, right? Reality might look a little different here, but the idea is to bring complexity down again. Now, what the book might or might not tell you is that usually the graph isn't as nice, and that is because you're not living alone with your source code. You also have impact in practice, which is budget concerns. Well, doing a refactoring means not producing features. So that has to be budgeted for. People are paid to do it. It has time concerns. Well, there's a deadline approaching and your idea is to go for refactoring right now. Do it after the deadline, because there won't be a second deadline, obviously. Yeah? You never have time to do bigger refactorings. You don't, I don't. And of course, there's risk. Because as you know, refactoring is changing the code without changing the functionality. I'm not asking for raised hands here because I don't want to blame anybody. But every now and then you refactor something without absolutely not changing the semantics of it at all, and still tests are failing. So it's just a hard thing to do. It has a risk to it, the risk of failing. What now? The situation may only improve slightly. We did our best, but due to these risks, it got hard to do it properly. So just a little less complexity, but still piling up. Now, my suggestion, if only we had a tool that allows us to do refactoring, but do it in small steps. Every time the tool points me to it, it finds refactoring candidates, whatever that might be, for your project. Copy and paste of source code, potential issues, code that seems to be less maintainable because it's spaghetti-like, it's a lot nested. It gives you right in your PR a small suggestion. The static analyzer finds a candidate for refactoring and tells you to do it. So what we want to do is do refactoring in all these little, tiny baby steps. Because then, of course, the risks are still there, the budget concerns are still there, it's still something you have to do. But it's much easier to carry the very, very small risk through your day-to-day work, through project management, and through testing. You just made it smaller, you just made it in tiny efforts. And that's exactly what a static analyzer can help you with, because in every time, in every PR, it can find that one smallish change that now is justified, now is a refactoring candidate, and now gets your code immediately at least a little better. I'm not promising there will never be a big refactoring needed, but if you do all the smaller ones, the risk and time consumption on the big one goes down. Can be leveraged immediately. This never, the code that has the small need for refactoring just never makes it to production, because you can immediately factor out these effects. So we've seen safety, or at least more useful, more likely to be correct code. We've seen increased potential for refactoring. Now let's go for improved security. Now I've said this is a non-critical system, but still security is an ongoing concern, right? You know that. Even without the Cybersecurity Resilience Act, and even more so with, security is a thing that will hit us all. that was many years ago that you could state, oh, I'm not a critical system. Say security, that's for, I don't know, cars and banks and the dangerous stuff. But nowadays, apparently everything is dangerous stuff. And we all fall under regulation that forces us to ensure security of our software. And it's not hard to search for things going wrong. So I did it just a day ago. Most prominently, cars that could be auto-updated, and now they are trackable via GPS. Well, they are supposed to be trackable, but now everybody can track your car, not you alone. There's also cars where you can make a key for yourself. That's nice if you lose yours. That's bad if somebody else can create keys for your car. And you see, I'm usually talking automotive, but the same pattern applies, I'm promising, to all of the other software out there as well. Also for user interfaces, because even if the user interface itself is your nice Qt-ish way to look into the application, it's also one of the most prominent ways of entry for potential issues, for potential hackers. Right? That's where your software communicates to the outside. So even if it's not the critical part, as in it does the functionality that shouldn't break, it's the entry point towards that functionality, and that we should protect. So I'm always arguing, and I'm with the Cyber Resilience Act there and all the other regulation, that security is, of course, a holistic approach. And I'm pretty sure I have a nice suitcase of techniques with me, and everybody's using at least some of them. Of course, for me, the biggest one in there being static analysis, not trying to talk down the others, but that's what we are doing, that's what we are offering. So how could static analysis help you with ensuring the security of your systems? The nice thing is, at least to some extent, that's an out-of-the-box experience, because these analyzers support multiple rule sets that cover security and safety, and the safety rule sets now are going into security as well. It gets harder and harder to distinguish those. Well, because if your braking system crashes and doesn't brake, it tends to be less and less important if it broke out of itself because it wasn't well programmed, or if it broke because somebody made it break. In the end, it did not stop the car, it didn't work. So security and safety have a biggish overlap there. And most of the analyzers just offer out-of-the-box tools that will improve security of C and C++ source code, be it the more safety-critical ones, the more security-focused ones, or if you want to go there, there's the CWE, which is the Common Weakness Enumeration, which is just it's basically a huge collection of situations your software could be in that are bad for security. And tools can pinpoint these. They can find it in the source code automatically and say what you are doing over there is using a bad seed for your cryptography algorithm, meaning even though your algorithm is fine, you're seeding it wrong, turning to, well, not being secure anymore. And of course, in the overlap, you have all of the nice, well-known ways to hurt yourself that turn into safety and security nightmares in the end, and that are hard to spot. But I'm pretty sure you know these, right? You're C and C++ programmers here. So you've seen out-of-bounds writes and reads. Let's go into maybe properties that are less commonly known. What does the CWE give you, and what could a static analyzer find automatically in your source code is, for instance, the CWE 337, which is something that is easy for an analyzer to find, but hard for a developer to spot. And why is that? The source code pattern itself is very simple. In principle, what the analyzer does is, for all initializers of random number generators, look at the argument and decide if that argument is easily predictable. That's simple from an automatic analysis standpoint. But a developer would have to keep in mind, who is initializing that? Am I that? Who's responsible for doing so? And given my platform, my glib, my system, my device, is that a predictable seed? Right? Is my random device on that CPU predictable or not? Am I in an environment where this is safe? In principle, that's an easy decision, but that's a big table behind it that tells you which combinations are valid and which are not. So easy for an automatic analyzer, hard for developers to keep in mind. The others, another one where an analyzer can help is CWE22, improper limitation of a path name to a restricted directory. What's that one about? Think of an upload feature. You can upload a file into your system and give it a name and a path where it should go. And now a hacker could have the clever idea, what if I put a path that does ... and I can play around with that, and can I manage to overwrite the etc. password file on the embedded Linux with my, this is just a picture of my face PNG. And here we are. That's improper restriction of the path. In principle, again, simple. You don't want the path to escape from a certain sandbox. Why is that hard for developers? Because it has to take the whole control flow into account, right? There's a user interface with an upload button somewhere over here, and then that path is sanitized and managed and moved and with the picture, and the actual problem happens over there. So you have to keep the whole control flow in mind. And that usually crosses a boundary of your competency, right? You're the person developing the upload feature, you're the person developing the storage stuff, and the problem just happens in combination of these two. And you need a very thorough overview of your system, which an analyzer has, but a developer usually has not and cannot have. I'm not blaming you, but nowadays we're building systems which are too large to be in the mind of a single developer. Last but not least, exposure of sensitive information to an unauthorized actor. And that's the whole description I copied, right? There isn't more to it. Some might say that might be an unspecified objective here. Let's throw it back to project management because they're just not telling me what I'm supposed to implement. And that's exactly the problem here. This can manifest in a multitude of ways, billions of ways. And if you're just reading, well, please don't leak information to unauthorized actors, that doesn't give you enough. But somebody who has done the threat modeling, who understands the system, who can classify what is authorized and unauthorized even meaning here, can create a configuration for an automatic analyzer that takes the developer out of the responsibility of knowing the magic behind the definitions. And an analyzer can look at the source code and pinpoint this data is unauthorized or is accessed in an unauthorized way because some reason, some data flow, some control flow behind it, and then developers can fix it. Again, that takes a lot of background knowledge. And again, I'm not blaming the developers here. That takes background knowledge that is created in the threat modeling process. Only parts of the development effort are in. But you can create analyzer rules that will automatically transport that knowledge to the developers in a hopefully understandable way without having everybody participate in every decision on how we determine authorization. So my suggestion, how will security be done using a static analyzer? And that's a 4-step process. And admittedly, the last step is go back to first step. So it's an ongoing process. Use the default routes. There's well-known security problems in C and C++. Without any configuration, tools can spot these because they are well-known. This is how things break. This is how you leak memory that could contain a password. Then go for threat analysis. Look at your system. Look at the trust boundaries. how does your data look like? Where is it stored? How may it flow? That's information tools cannot have, right? It depends on the project. We need to know how your projects are supposed to look like. How does authorization even happen? But once this is determined and the threat analysis and threat modeling, the Cybersecurity Resilience Act makes this a thing. It needs to be done if you're falling under it anyways. So why not take the knowledge that you have collected about potential security issues in your system and create customized rules for a static analyzer? Why have this only on paper in Confluence? And then every time telling people, oh, now you got to look it up and now you got to figure it out. And now it has changed. Why not create a system that will tell you right in your pull requests what you decided here is a problem, manifests in your source code, so please fix it right now. And never have the problem again and not wait for half a year for the security issue to manifest. And of course, this is security, so you will never be in a secure and safe space. I'm sorry. You got to start all over at the first step again once you got this done at least once. So maybe let's take a step. This can also help manual reviews. Because you know that manually reviewing source code is time-consuming, it's imprecise. It's often hard to find reviewers that have the necessary system-wide knowledge to actually assess the impact of your code change. It might be fine for the test case and pretty locally, but system-wide it could break stuff. And of course, it needs to be done repeatedly. So let's introduce static analysis into our reviews. And I'm just going for a screenshot here. Basically, what you could do is have a tool that comments into the pull requests, just like a human would do, except that we are taking out at least parts of the human error. Maybe some of you have review guidelines. Every time you do a review, please watch out for the following things in the source code. And then every now and then, it's Friday afternoon, you got to be quick about it, the release is approaching, or the guidelines have changed, there's another problem. So why take the error of having human errors here, instead have a system that does exactly that, with thoroughness, automatically and exhaustively, and right in your pull request says, well, your guideline says there needs to be a block statement here, so do it. Hopefully this is all already handled by your auto formatter. But just to have an example that is simple enough. It could be more complex, and of course it could again be tailored to your needs. Whatever has been a hurtful, bad thing in the past of your project, source code that you now try to spot in every review because you know it will be a problem, why not spot it automatically instead of going there? Okay. Let's summarize then. The right tool of the job is for you to determine linters, bug fixers, bug finders, or conservative tools. I cannot tell you. It might depend on your project and your property. There's benefits also in non-critical projects. All of the benefits I've mentioned can be there. And the batteries are mostly included. Go take a tool, use what's there out of the box, which takes you pretty far already. And once you fix these issues, once you get your flow working on these ones, see that you go for the more advanced stuff customized for your project and continue there. Thank you.